Hello, very good morning to every one of you. So today we are going to continue with the third part of the chapter 4 video, where in the beginning of the video today, we are going to first talk about electrical conductivity of the period 3 elements in here. All right, so here we go. Showing to you in the graph here is the electrical conductivity across period 3, where you have for the first elements up here, this is the conductivity of sodium, magnesium, aluminium. We have silicon, phosphorus, sulfur, chlorine, and also argon. Okay. Okay, so you can see that from here, sodium, magnesium, aluminium are generally good conductor of electricity. Silicon is somewhere in between here. That's why we call silicon as a semiconductor, while phosphorus, sulfur, chlorine, argons are what we so call as an insulator. So how are we going to describe the electrical conductivity of the period 3 across them? So let's have a look together. Okay, so it says that conductivity of the period 3 increased from sodium to magnesium to aluminium. Okay, so since all of them are metals hold by strong metallic bond, okay, so we must describe them as metals that hold by strong metallic bond, which make them a good conductor. So then you write the valence electron, where aluminium has the valence electron of 3s2 3p1. It's the best conductor, followed by magnesium with the valence electron 3s2, while sodium with the valence electron 3s1. So since aluminium has the greatest number of valence electron, so it can delocalize more electron. Okay. So therefore, the metallic bond strength increased from sodium to magnesium to aluminium. So you are going to first use valence electron, greater the number of valence electron, greater the number of electron delocalized, greater the strength of the metallic bond, therefore higher the electrical conductivity. Now, same things that you can use to describe the melting point of the period 3 elements here, right? So this is what happens for sodium, magnesium, aluminium. Okay, then we have silicon. So silicon is a semiconductor since it is a metalloid with a small band gaps in between the valence band and also conduction band. Okay, so we've already talked about this inside previous chapters. So if you want to understand what makes the valence band and conduction band, you can review back on the chapter 3 video. So this conductivity activity can be increased by two methods, either by increasing temperature or doping with other elements such as boron and phosphorus. Okay, so this is the for semiconductor. And finally, we have an insulator. Okay, so phosphorus, sulfur, chlorine, argons are non-metal, which makes them a good insulator since there are large band gaps between the conduction band and also valence band here. Okay, right. So with that, that is all the things that you need to explain about the period 3 physical properties. So previous video we have already did atomic radius. We also discussed about melting point and also enthalpy change of vaporization, followed by ionization energy, the successive ionization energy where you can make use of them to predict the position of the periodic tables. Okay, and today we end up with electrical conductivity of the period 3 elements. All right. So finishing physical properties, let's move on to the next one, where we have the chemical properties of the period 3, where in this subtopic, we are going to discuss the reaction of the period 3 with oxygen and acid-base properties of the oxides. Okay. So here are the objective of the lessons today. So you are going to describe the reaction of elements with limited excess oxygen, explain the reactivity of metal oxygen, describe the reactivity of oxide with water, explain the acid-base properties of the oxide, including the type of bonding, and then deduce the oxide-base amphoteric or acidic based on their characteristic and their reaction with acid and base, and then explain the use of the sulfur dioxide food preservations. So without further ado, let's have a look at the content. Okay, showing to you in the first is the video or is the tables of the basic chemical properties. So we have proton number and their valence electron respectively. So it is 3s1, magnesium is 3s2, and 3s2, 3p1, silicon 3s2, 3p2, phosphorus 3s2, 3p3, sulfur 3s2, 3p4, chlorine 3s2, 3p5, and argon is 3s2, 3p6. Okay, so because in the early part of the periodic tables. So sodium, magnesium, and aluminum has a tendency to form cation, whereas in the later part of the periodic table, we have phosphorus from phosphide, sulfur from sulfide, chlorine from chloride. Okay, so why is this happening? Because going across the period, ionization energy and electron affinity increase at the same time. So in other words, when you're going across the period tree, you have a low ionization energy. Low ionization energy makes the elements in the left group, group 1, group 2, group 13, they have a greater tendency to donate electron, hence become a positive. So as going across the period also, we have ionization energy become increased. That means it's difficult to donate donate electron, sorry. At the same time, we also have electron affinity increasing. So in another word, the easiness to accept the electron increase. So that is why elements in the right group of the periodic table, for example, group 15, group 16, especially group 17, they have a greater tendency to accept electron. That is why you see in here chlorine can easily become a negative charge instead of positive charge. So this is further supported by their standard electrode potential value, E naught value, where main sodium in here, being the one with the lowest ionization energy, has the highest negativity of the E naught value. Therefore, sodium in here acts as the strongest reducing agent, followed by magnesium and then aluminium. Whereas chlorine in here, being a high electronegativity and high electron affinity, so it can act as a strong oxidizing agent in here. So this is how we are going to deduce the basic properties of the period tree elements. Now, because of all these specialties given by sodium, magnesium, and aluminium, they are suitable to be used in industry for certain process. Okay, so for example, okay, magnesium is often used as the extraction of titanium. Aluminium is used in the thermite process to extract chromium. Okay, and then chlorine is suitable to use to extract bromine out from the seawater. Okay, so all of these have to do with the strength as a strong reducing agent here. Okay, so this is how the informations of the E naught value can help us to evaluate which one has the strongest reducing strength and which one has the strongest oxidizing strengths. Okay, so just a brief of how we read the E naught values here. So to look for the strongest oxidizing agent, okay, let's start from the oxidizing agent. So to look for the strongest oxidizing agent, we look for the E naught value, which is the most negative, most positive, sorry, and or least negative if all of them are negative. Okay, and then you look at the species at the left side. Okay, so for example, in this case, chlorine is the most positive E naught value. So that's why chlorine in here acts as the strongest oxidizing agent. Okay, now this is how we read for oxidizing agent. And conversely, how are you going to treat as reducing agent? Okay, we are looking at strongest. Huh? Okay, so you read from the E naught value, which is the most negative or the least positive. Okay, then you read the species at left, at right, sorry. So in other words, in between sodium, magnesium, aluminium, and chloride ion, it says that sodium is the strongest reducing agent. Why? Because it has the most negative E naught values among all of them. So that is how we are going to read the strength as oxidizing agent and reducing agent here. Okay. So I hope that you can get it. For more details, we will learn it more in the semester 2 for your information. Yeah. All right, so showing to you in here is the summarized table of the chemical properties of the reaction of sodium with their oxygens and then their properties inside them. Okay, so where we have sodium, when we add with oxygen, we mostly form sodium peroxide first. Okay, so this is the most common species. And when you further heat up, then the peroxide will eventually become oxide here. Okay. So both of these oxides has a high melting point because they are ionic compound with a basic characteristic. Whereas magnesium, when burned with oxygens, will form magnesium oxide according to the equation. So it is also an ionic oxide, and among all of these oxides, it has the highest melting point here. Aluminium form aluminium oxide according to the equation 4Al plus 3O2 give 2Al2O3. So aluminium oxide is an ionic compound with high covalent characteristic. Therefore, it is amphoteric oxide. Okay. While silicon form silicon dioxide here. Okay, according to the equation, Si plus O2 give SiO2. So silicon dioxide, for your information, is a covalent compound here, and therefore it is acidic. Okay, so for phosphorus limited with reacting with limiting air. Okay, if it is a limiting air, you form phosphorus trioxide. And if you're reacting with excess air, you form phosphorus pentoxide. So both of them are simple covalent molecule hold by weak van der Waals forces, which we'll explain later. Sulfur can also form two forms of oxide, where you form sulfur dioxide and also sulfur trioxide. So when sulfur is first heated, it will first form sulfur dioxide. And when you heat it with excess air, sulfur dioxide will further oxidize to become sulfur trioxide. As for chlorine, chlorine does not react directly with oxygen. However, chlorine oxide can be prepared by reacting with the mercury oxide with chlorine, according to this equation. And to form Cl2O7, it is formed from the chloric 7 acid, where you undergoes dehydration to form the Cl2O7. So all of them are simple covalent molecule hold by weak van der Waals forces. So that is why they acidic here. So this is just in the beginning of the summarized table. So we are going to have a look in details for each of these oxide and their properties in our next video. Okay. So I think I'm going to end my lesson for video for this part, and I'll see you all in the final part of the video. Right, with that, thank you very much.